Okay, so this is section 1, part 2. Last day we looked at the exponential graph and what it looked like. We introduced you one simple application. We're going to show you a whole bunch more today. Now I know last day the application we used was modeled using the exponential equation y equals to c to the power of x. Remember last day the hydrogen one was like 1/10 to the power of like x or p, but most of them actually don't use 1/10 or c to the power of p. They usually put a number in front, which is a, which stands for some initial value. Okay, so your initial value doesn't always have to be 1. It could be 10,000, 500,000, and that's why the more, I think, more common one we use is y equals to a times c to the power of x, where a is some sort of initial value. And to illustrate this, let's take a look at example number 1, where our biology teachers here are trying to grow bacteria. And initially, they start with 5 bacteria in a petri dish. Mr. Lamb's petri dish triples in every hour, or at least the bacteria does, not the dish. The bacteria triple every hour. And so the question will be how much bacterium will there be after 6 hours? So if we're using that application of exponential formula here of y equals to a times c to the power of x, we have to identify what all these things mean. Y is our result, so that's pretty much the amount of bacteria, AMT, or amount of bacteria. A seems to be our initial value, so how many did we start with in this case? Yes, 5. C, now the C is that constant that represents that growth or decay. In this case, bacteria is growing. And what is the rate of growth in this example? Well, it says it triples every hour. So that means our C, our growth rate, okay, so C is our growth rate, that must be triple or 3. And since X represents, I guess in this case, time, we'll say the time here is 6. So X here must represent the time. The time it takes to triple. Or not the time it takes to triple, the time it takes to look at how much our bacteria grows. So I guess we've got our nice little formula. We've put in our numbers, and now we just have to evaluate. Now notice there's multiplication and exponents. From BEDMAS you learned way back. BEDMAS stands for brackets, then exponents, then division, multiplication, which is the same level, adding, subtracting, same level. We better do the exponents first. So let's do the 3 to the power of 6 first. I don't really know what that is, so I'll bring out my calculator. 3 to the power of 6. That's 729. And if I multiply that by 5, it looks like I'll have 3,645 bacteria. Quite a bit. Okay. Now, let's take a look at the next part. So here it says bacteria in Miss Samra's petri dish triples, so it triples again, but this time it's every 2 hours. So this is a difference, and let's take a look at how that changes. Okay. In the previous example, it triples every hour. So if you think about it, after 6 hours, it tripled 6 times. So 3 times 3 times 3 times 3 times 3. That's why we have exponential growth here. However, this one, it doesn't triple 6 times in every 2 hours. Something happens. So in this case, let me write down the formula again. We're still starting with 5 as the initial one. We still have a rate of growth of 3. But in this case, X is still time, but notice it triples every 2 hours. So I can't just use X, I have to do something to it. So let's think back. In the previous examples, 6 hours, okay, and it tripled every hour. That's why it was 3 times 3 times 3 times 3 times 3 times 3 times 3, or it tripled 6 times. In this case, I have 6 hours once again, but it only tripled every 2 hours. So if I were to draw a picture from before, right? Here's my timeline. Here's 0 to 6, right? 1, 2, 3, 4, 5, 6. It triples 1, 2, 3, 4, 5, 6. My timeline for part B, if you think about it in this case, 0 to 6, 1, 2, 3, 4, 5, 6. It only triples every 2 hours. So once here, and once there. So it's no longer x is just 6, but you see it's every 2 hours. So we have to actually divide that time by 2 because it takes 2 hours for it to triple once. So this is my equation, and therefore it's 5 times 3 to the power of 6 divided by 2. 6 divided by 2 is just 3. So that's 5 times 3 to the power of 3. So you see how there's only 3 times that it triples? Versus the previous one, there's 6 times it triples. So 3 to the power of 3 is just 27. 27 times 5 gives me 135. So notice much slower bacteria growth. Okay. By the way, I've showed you some important things here, especially with this last part B. I'm going to try to show you over here in this corner, maybe just a general form, the most general form of an exponential function. Okay, and it's y equals to a times c, some sort of rate, and instead of having just x, I'm going to go x divided by t. Okay, now let me tell you what these things mean. Y, of course, is the final amount, right? What you get in the end. A in this case is just your initial amount. Okay, what you start with. C, of course, is just the rate of growth or decay. Please write this down. And the x is just the time, the total time that's passed. And the important one is that capital T, I'll say that's the time needed to complete. I'll say one, and I'm running out of space here, sorry, one cycle of the growth or the decay that is going on. So in this example, it takes 2 hours to complete one cycle of growth. Therefore, t equals to 2. Okay? If you got this formula in your head, then this section should be pretty straightforward. Okay? Let's look at example number 2 now, when you're ready. This one talks about the population of mosquitoes. Yuck, I hate mosquitoes. That's why I hate camping. And it says here the population of mosquitoes decreases by half. Okay, decreases by half each night that the temperature drops below 2 degrees Celsius. So that's why I guess they freeze to death. Who knows? But it says write an exponential function to model the proportion of the population remaining. That's P they use after n nights of freezing temperatures. Okay, so all these letters confuse you. Let's go back to what I've put in the box. Okay, we're going to start with y, which of course is our final amount. Okay, and we have a, our initial amount, c, our rate to the power of x over t. Okay. In this case, let's take a look at what y represents. Well, y is the final amount or the final population. I've chosen to use the letter P to represent that, so that's P. We don't really know what the initial population is, but if we're talking about proportions, I can use percentages, so I'm just going to use 100%. Okay, that's a starting amount. Okay, proportions, I can use percentages. Our C is the rate of growth or decay, and because the population decreases by half each night, I guess that's a rate of decay, and that'd be 1/2. And we have X, which stands for our time. In this case, that would be the letter N. And it says it decreases by half each night, so the time needed to complete one cycle is just one night, so N over 1. Or if you want to write it again, we can write it as P equals to, and I'll once again use 100%. You don't have to, though. You can just use 1 and raise to the power of N. Okay? I use percents because in part B now it says, after how many nights will the population be below 10% of its original size? And so to do this one, what do I have to sub in? What really is 10% of its original size? Well, that must be the ending or final amount. So I'll take our formula P equals to 100%, 1/2 to the power n. I'll replace P now with 10%. And I'm going to try to put all that together. 10% divided by 100%. Well, that's just actually 1/10 or 0.1. So here's what we have. 0.1 equals to 1/2 to the power of n. And our goal now is to see after how many nights you have to solve for n. And to do this, we really can't using algebra. So that's why I said you may want to graph this out with a graphing calculator. And for those of you who don't have a graphing calculator, well, guess what? I think all you can do then is guess and check. Okay? I will graph it out with my graphing calculator. Bring out yours if you have yours. To graph something like this out, I'm going to ask you to do a y equals 2, and I'm going to ask you to separate this into two equations. I'll use 0.1 for the left side, and then 1/2 in brackets raised to the power of x for the right side. Don't do anything yet in terms of graphing, but let's just change our window. Remember, x or the n stands for the number of nights, so the minimum number of nights is probably 0. Don't really know how far I could go, but I'll just take a look at, I don't know, say 12 for now. Scale I'll just use as 1. Now the y values, remember this is the exponential graph, and from last section the smallest y value would be 0. Yeah, right, that's where the horizontal asymptote is. The largest one I don't know, but since we started with like 100%, that'd be 1, so I'm just going to use 1. And I'm going to now graph it out and let's see what we get. There's our 0.1. Oh, lovely. Here's my decay function, and because I want to solve it, I'm looking for the intersection point. Okay, let me actually just draw this out for you first. Okay, so you do the same thing in your notes, please. Okay, solve for n. I'm going to use the graphing calculator, or just guess and test, guess and check. Okay, got my lovely graph. I think my x coordinates were 0 to 12. My y coordinates for the window were 0 to 1. Then I had this lovely graph, there's 0.1. And then I had this lovely graph, the exponential, whee! And I'm looking for the intersection point. So on your graphing calculator, go ahead and find it. I'll do it on mine. Second, calc. Choose number 5, intersect. To ask you for the first curve. Yep, I'm on that horizontal curve there. Sure, press enter. See, I'm on the second curve. That's the exponential. Yeah, I'll press enter. I'll just press enter for the guess. Let the calculator do the work. And x equals to 3.3. Okay. So, therefore, 3.32. 3.32 comma 0.1. So therefore, I said how many nights? Well, if we go back to my calculator, 1/2 to the power of 3.32 nights is approximately 1/10. It'll take me more than 3.32 nights, so I'm going to round up. It'll take 4 nights. Okay. Now, will the population ever reach 0? Looking at that blue graph, it looks like it's closer and closer to 0, but because we have that asymptote, technically it won't. So, technically, no. No. It'll get smaller and smaller. And if we're looking at the math part, it'll be like 0.00001. But in terms of context, in this context, 0.001 mosquito is pretty much like nothing. So in this context, I'll say yes. Eventually, the numbers get so small that the mosquitoes will eventually, once again, eventually reach 0. Just like I like it. Yeah. All right. Okay. So I'll give you a chance to copy this down, understand this example, and then we'll move on to page 2. Okay, here's another type of exponential equation or function that you'll see. Here, I'm telling you, you've got $100 in a bank account and you want to invest it. And the bank's nice. This bank is really, really good. It pays you 6% interest per annum, and it's compounded annually. So in this case, I want you to tell me or create an exponential equation, graph it out, and then use it to estimate when you should expect your money to double. So tell me how long it takes for you to get 200 bucks. A few things here, okay? If we're going to use that equation, y equals to ac to the power x over t, we have to kind of figure out what all these things are in this example, okay? Y seems to be your ending amount. Okay, ending amount. A, in this case, is your initial amount. C is your rate. Now, think about what I mean by rate. Okay, a 6% annum compounded annually. What does that mean in terms of how much you're going to get at the end of annual means 1 year? So at the end of 1 year, you'll get an extra 6% in interest. So you'll still have your original amount, but you'll get an extra 6%. So the actual percentage, I'll say total percentage, is really the original 100% plus an extra 6%, which is really 106%. So in that case, our rate, therefore our rate here, of rate of growth or decay, written as a decimal, will be 1.06. And that's the value of C. Okay, so this equals to C. All right, that's your rate. Now, X, of course, is time, but then T in this case is the time it takes for one of these cycles to get through. And because it's compounded annually, T would be just 1 year. Okay? Because it says compounded annually. So, as a visual, imagine like at T equals 0, then 1, then 2, then 3, then 4, then 5, then 6. You're getting interest at all of these moments in time. Okay? So let's see what the exponential equation would be. So the ending amount, y equals to the initial amount of $100. C is my rate, 1.06, to the power of x, which is just the time, over t, which is 1. So there's my equation. And because I'm saying find x when it doubles, so I'm saying if I make y equals to 200, go ahead and find out x for me. I will do some quick algebra by both dividing both sides by 100 first. So you get 2 equals to 1.06 to the power of x. And it's using this equation now that I will actually graph and solve. So graph and solve for x. Okay. If you can't, you're going to try to guess and check. So here we go. I'll go y equals to, turn the calculator on first. It's no longer 0.1, it's 2. I'm starting at 1, so 1.06 to the power of x. Better change my window this time. I guess, I don't know, go to 20. Y min is, well, I want to do at least 2. By the way, I just realized I don't have to actually use the equation in purple. I could have used the equation in black, been the same thing too. It's just my y values would change a little bit. So here it is. Here's the 2. Here's the growth 1.06 to the power of x. And I want to solve, so second calc. Just find the intersection point. Bam, bam, bam. Oh, 11.89, so 11.9. So in this case, you graph it out. So from the graph, it looks like it takes 11 point, what is it, 89 was it? 11 point, yeah, 8, or how about just 11.9? 11.9 years to have your money double. That's a lot of time. So how can I make it faster? Well, what about if I went to a bank that said, let's compound it semi-annually? Now, what does that mean when I do it semi-annually? So here's my timeline again. 0 to like who knows what. So 1, 2, 3, 4, this is 5. Semi-annually means I get interest twice a year, but I don't get 6% each of those times. I get half of that. So compounded annually means I get a 3% extra bit every single time it compounds. So the difference here now is that the total percentage is not just 6, but it's only 3. So 103%, or your C value is now 1.03. Okay. There's also something different here. The time here is not 1 year anymore because it compounds semi-annually. That means it's half a year. So my capital T is actually 1/2. So let's see what happens with my equation. Okay, y equals to, I'm copying it just from above, y equals to 100 because everything else is the same. 100. The rate now is different, so it's 1.03, and it's to the power of x divided by 1/2. Now, x divided by 1/2, dividing by 1/2 is the same thing as multiplying by its reciprocal. So I'd rather you write it like this: 1.03 to the power of 2x. Okay, and this is the equation that talks about this situation when I've compounded it semi-annually. Notice the differences are here in the exponent and also in the base. Now let's estimate when I should expect my money to double. In this case then, of course, that just means y is 200. Now, you know how I said earlier I should divide by 100? Well, let's pretend to be lazy, and let me just leave it like this. And if I had just left it like this, and I asked you to graph and solve for x, how would you do it? Okay. Well, just listen to me first, and then you can go back and try it on your own. I'd go to my graphing calculator again. Instead of 2, it'd be 200. And instead of just 1.06, it'd now be 100 times bracket 1.03, close the bracket to the power of, and be careful here, I want a bracket around the 2x because the 2x is the entire exponent. In this case, I'm going to change my y mins because no longer is 3 enough. I'm looking at 200, so maybe make $300. And let's see what happens when I graph. There's the 200. Here's the exponential growth function, and just like the previous one, I'm going to find the intersection point. Second calc, intersect. $11.7. Oh, so yeah, not too bad. In this case, it says it takes 11.7 years to have your money double. And so I guess that just means I save a little bit of time. Not too much, but I save a little bit of time. Okay? Alright. Now, besides compounding annually and semi-annually, sometimes you'll see compounding quarterly, which means, of course, it's what, 4 times a year? Monthly, which is like 12 times a year. Weekly, which is like 52 times a year. Or even daily, how about 365 times a year? And even continuously, like every second. Okay. Now, this can change the equation that I have in the box up here. But how can it change, or what parts change? So let me try to illustrate to you the general form of what we've got. Okay. Once again, we'll go back to my start. Y equals to AC x over t. Okay. And now here is the general form of these compounding problems. Okay. A lot of times, instead of using y, they'll now use the letter a for the final amount. Okay. So a equals, sorry, let me just write it out first. Okay. A final amount. In money problems, the initial is called the principal. The principal amount, or the starting amount. Now, this rate here is always interesting because it's always a decimal, and we talk about that total percentage. So we take 100%, or that's just a decimal as 1. Then you add to that interest you get, so the interest rate I'll call I, but you have to actually divide it by n. Excuse me. That's the number of times that the amount actually compounds per year. So in our previous example, you see how I took the 6% and I chopped it in half because I have compounding twice a year. So I'm chopping in half, dividing by 2. I just called it divide by n. So let's just write down this first. I, of course, stands for the interest rate. N is the number of compounding periods. So how many times it compounds per year. And then now, instead of the x over t, the x is our time. We use the letter t to represent that. That's small t. And that capital T is, of course, that rate, or the number of times it compounds. So that gets flipped around, and notice from above, you see how it was 2 because it's compounded twice, so it's 2 times x. So in this case, it'd be n times t. Okay? So the little t here is just the time in years. Okay? So it's still kind of like that base function we had before, but this is just the one that the compounding business people seem to use more often. Okay? So if you see a question like that in your notes, you can use this structure. All right, let's move on to page 3. Do 2 more quick examples, and then we'll be done for today. So here, I've got an example where we're talking about A, diving below the surface of water. Don't know if any of you did that before, where you go dive, 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 but you get darker and darker and darker as you get further and further below sea level. So in this case, for every 5 meters that a diver descends below the surface of water, the light intensity is actually reduced by 8.5%. So write an exponential function that relates this. I'm going to go back and use my general form, y equals to a c to the power x. Seems like we're starting with 100%, so I'll write down a as 100. C is the rate. Now in this case, it looks like it's decay because it's reducing by 8.5%. So C seems to be, if I take 100%, reduce it by 8.5%, that leaves me with 91.5%, or a C value of 0.915. Remember, it always has to be a decimal. Raised to the power x, that's cool, but it says for every 5 meters, so that's the amount that it takes, or I guess I'm dividing this by 5, is what I'm trying to say to you, okay? Because it takes 5 meters to complete one of these cycles to reduce it by 8.5%. Okay? So there's my equation. There's my exponential equation. What percent of the original intensity remains at 10 meters below the surface? Well, I guess I'm asking for y, which is the final percentage. In this case, I'm given the value of x, which is 10. So 10 divided by 5. That means I'm reducing it twice. That's why it's 0.915 to the power of 2. On your calculator, let's go ahead and do that. Of course, it's 0.915 squared first. Then we'll multiply that by 100 to get our percentage. And it looks like 83.72%. So that's the percentage of light that remains at 10 meters below the surface. Still not too bad. Well, now I'm going to ask you to use a graph, or once again, guess and check to estimate how far below the surface the diver would be when the intensity in this case is 40%. That should be of the surface. Okay, so back to our original equation. Going to replace now the y value with 40%. That's my neighbor's dog, by the way. He seems to be in pain. Can't help him out. I'm doing math. So 40 equals to 100, 0.915, x over 5. Now once again, you can just use this equation to plug it in. Or if you want to make it a little bit nicer, I'll just ask you to divide both sides by 100. You get 0.4 equals to 0.915, all raised to the power of x over 5. And then this is where I'm going to ask you to graph it out. And of course, find the intersection point. Okay. Go ahead and do that now, please, on your own. And let's see if you get the same answer as me. Change your window in this case, because your y value doesn't need to go from 0 to 300. It's just everything's less than 1, so I'll just go to 1. Let's see what we can get. Oh, there it is, there it is, there it is. Oh, yeah, yeah, yeah. Uh-oh. Looks like I need to extend my x value. I don't know, let's try 100, I guess. Oops, that's way too much. Oh, that's better. There he goes. There it crosses right there. So we just have to find out that amount. Second calc. Intersect 5. First, second, third. Oh yeah. 51.6. So it looks like here x equals to 51.6 meters. I guess that'd be below the surface level. Okay. There you go. Alright, example number 5 is pretty much the same. I'll let you try that on your own, and I'm just going to be quiet now while you take a look. I will write down the answer at the end. You can double check on your own. Okay? Alright, go for it. If you're stuck right now, here's a clue. Y equals to, yep, that same form, a c to the power x over t. If you think about how much we have at the beginning, it's 1, I guess in the end we're saying it's 1/25th of its original mass. So 1/25th of the original mass. I don't know what we call the original mass. about 1/25 of m, the original mass. So m stands for the original mass. Don't really need that. You can just use the number 1 if you wanted to for m. It doesn't matter. Or 100 or 1,000, whatever. It's up to you. Notice, I guess that means a, which is my original mass, should be m. And that's why the m's cancel out, by the way. Okay. C is the rate. In this case, it's exponential, not growth, but decay, because it's the half-life. So my rate is a half. And since it takes 12 days to do it, or that one cycle, that means the capital T must be 12. Or I guess x just stands for the number of days. So x equals the number of days. Now, once again, you see why that original mass doesn't really matter. Because look, the m and m's can cancel out, so ultimately you're left with this equation. 1/25 is equal to 1/2 to the power of x over 12. Go ahead and solve it now with your graphing calculator or by guessing and checking. I will use my graphing calculator. 1 divided by 25, and that'll be 0.5 all to the power of x over 12. See, just like before, right? Straightforward. Whoops. There's the 1/25. Wow, that's hard to see. Oh well. Let's figure it out anyways. Second calc. Intersect. 1, 2, 3. 55.73. So x equals to 55.73 days. And I guess that would be how many days for substance to decay to 1/25 of its original mass. Alright, this was long. Sorry.